Good morning. It gives me immense pleasure to be here again for my course, Aircraft Stability and Control. Today, I am in lecture number 10. The topic of today's lecture is neutral point and fuselage contribution on longitudinal static stability. I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. In today's lecture, we have few topics. This lecture will cover the following topics: understanding the neutral point, understanding the static margin, change in longitudinal static stability with CG location, use of reflex airfoil and the neutral point, and before that it will give for the tail contribution for the static stability. So I will go with the neutral point, stick fixed. So before I start, I should just revisit the lectures. In my previous lectures, I have started with definition of stability, different motions. Out of that, few motions are statically stable, few motions are dynamic stable. Then I have seen a spring mass system for explanation of static stability and the dynamic stability. In that, I have shown that a system which is spring and mass, and if it is moved in a vacuum, it will start vibrating and it will keep on vibrating because it is not damped. So this system, every time, it is the tendency of this system is to go towards its origin. So it is a static stable. So just I can draw here one small this is the one case where I can put the spring here like this, and this is the mass, and this is the spring constant K, and if I move from here to here, this is the X. So this spring, after movement, it will try to move like this and like this, like this, like this. So every time the tendency of this mass is to come to its neutral position, and so this tendency is called the static stable. Static stable case. In this only, if I put some liquid here, so what will happen? It will vibrate from here to here. After disturbance, it will go like this. Slowly, its amplitude will start reducing, and due to this damping, it will come to its neutral position after some time, and this is the amplitude. So this is called the dynamic stable. In previous classes, we have also discussed about the contribution of wing, contribution of tail, and we have seen that if we are putting like this, this is the wing here, and this is the tail. The effect of wing is Cm alpha positive and Cm naught also positive, but we don't want Cm alpha positive, we want Cm alpha negative. We have to use a tail, and tail will generate a Cm alpha tail negative, and this alpha tail will be countered by this. This alpha tail will counter Cm alpha of the wing, and this will be balanced. So the system will be statically stable, and also Cm naught will be positive. If you take this Cm and this is the alpha, Cm naught will be positive if we are using the this type of configuration, but here Cm alpha is also positive. But if we fix a tail here, this is the tail and this is the wing, tail will be in the negative direction and your Cm alpha of the whole aircraft will be less than 0. So this is the which we have learned, the contribution of tail, contribution of wing, and we have seen that how much the AC, the location of AC and the CG. If this is the CG and this is the AC, how much distance, how much difference between AC and CG should be there, and what is the position up to what location CG can come behind so that your static stability is maintained. So this is the point of neutral point, and we are going to discuss in detail about this point. And that is called the neutral point. Here I have mentioned the stick fixed because most of the cases till now and further also we will be studying about the stick fixed. Stick fixed means there is no variation of the control surfaces due to aerodynamic forces. It is fixed in a one point and it will remain in that point till it is not disturbed. So if you see here, this is the elevator, this is the horizontal tail and this is the elevator. And if you see here, if we change the angle of attack, this elevator will also produce some lift, and this lift will try to move this thing up and down. We are not considering this flexibility. We are not considering this flexibility of the control, and we assume that stick is fixed. In our whole cases, till the time we are not specifying especially that it is a stick free, all the cases which we are studying and we are deriving the equations of stability, all are for the stick fixed case. So this we have to understand first. So I am going to define first neutral point. The neutral point is defined as that point on the longitudinal axis of the body where the aerodynamic moment does not depend on angle of attack. Okay, so this we can see here that if this is the longitudinal axis and this is the CG location and this is the AC location, and if we start shifting from here, one position will come where CG will be also on top of this CG. So this position, when the CG is on top of the AC or both are coinciding, that time there will not be any effect of aerodynamic angle or the angle of attack, and if you plot the Cm versus alpha, movement will be constant for this is the dCm by d alpha will be 0. So this is this point where the aerodynamic center and the center of gravity are coinciding, and there will not be any aerodynamic moment with angle of attack. That position is, that point is called the aerodynamic, that point is called the neutral point. We are in this lecture, we are going to discuss about this neutral point. One question I want to raise before I start: are the aircraft aerodynamic center and the neutral point the same thing? Just I am going to clarify here. The aerodynamic center and the neutral point NP both are directly related to the longitudinal stability of an aircraft. Both these points are distinctively different when considering stability of the aircraft. It is the center of pressure that is considered to be the same theoretically as the aerodynamic center. CG and neutral point are not same, but for the symmetric airfoil, the center of pressure and the aerodynamic center can be assumed as a same. All the forces acting on the aerodynamic center or the center of pressure and the neutral point, when coupled with the downward force of the elevator or horizontal stabilizer, define the longitudinal stability of the aircraft. So the longitudinal stability of the aircraft is depend upon the position of the neutral point, aerodynamic center, all the things. As one may know that the lift force act through this center of pressure, which can be coupled with the center of gravity force and will provide a nose up attitude to the aircraft. This nose up attitude is compensated by the nose down coupled form due to elevator force and the CG position. Hence, for a stable flight, these couples are in balance. Okay, so we have to see that every motion of the aircraft is here. This we can see. Aerodynamic center is here. Center of gravity is here, and the aerodynamic center of the tail is here. So the moment which is produced by forward position of the aerodynamic center will be nose up. So this tail has to provide a upward lift force, and when this lift force multiplied this distance, that is the tail moment arm LT, with respect, it will make aircraft stable. So center of gravity and these things we have to understand very much clearly. And if the center of gravity is placed at the neutral point, the coupled force will be balanced so that when the aircraft is disturbed in attitude, it will remain in that position until corrected. Hence, the aircraft will be neutral, longitudinal, stable. So, I have here just explained in this case. So, if you shift CG like this, and if it is on top of this AC, so there will not be any moment and it will maintain the same position as it is disturbed. That point is called the neutral point. Okay, now I am going to derive the equation for the neutral point. The center of gravity location at which Cm alpha is 0 is called the neutral point. If I want to find the neutral point, then I have to make Cm alpha is equal to 0. If CG moves towards aerodynamic center and both coincides, then it becomes neutral point. We know the equation now. So here just you see in this diagram, this is the aerofoil, and here the center of gravity is ahead of the aerodynamic center, and if it start moving towards this, and when it is reached on top of this becomes neutral point. Okay, so we have seen that in our derivation of total coefficient of moment of the aircraft. So this is the Cm alpha of aircraft is equal to CL alpha of the wing, XCG by C bar minus XAC wing by C bar minus neta VH CL alpha T 1 minus D epsilon by D alpha plus Cm alpha fuselage is equal to 0. It means the total coefficient of moment or dCm by D alpha of aircraft, if it is balanced, no moment, 0, then we can say the point of the CG, this XCG will become XNP when we make it 0. So we have mentioned here this equation as a 0. Now this XCG has become XNP. So XNP by C bar is equal to this X. So if it from here we have taken here. So this is neta VH Cl alpha T and divided by Cl alpha W 1 minus d epsilon by d alpha. We have neglected this. The effect of this thing we have neglected. So here we can see x ACW by C bar minus Cm alpha Fs Cl alpha W plus neta VH Cl alpha T, where T indicates the tail and W indicates for the wing, 1 minus d epsilon by d alpha. So by this equation, it is very much clear that the neutral point is depend upon the aerodynamic center of the wing, aerodynamic center of the tail, coefficient of lift of the tail, neta, it is the ratio of dynamic pressure of the tail and the dynamic pressure of the free stream velocity. VH is equal to, here VH is equal to ST LT by S C bar. So this is the volume ratio and this is the volume of tail and this is the volume of the wing. This is the tail. So this volume is very important, and by this variation of this VH, we can vary the position of the neutral point. So CG should be little ahead of the aerodynamic center of aircraft. It depends on the AC on the wing, not the CG. Okay, so this you can see here that in this equation, there is no CG location, only AC is there. So the neutral point is depend upon the aerodynamic center, not the center of gravity of the aircraft. That we have to keep in our mind. So now next point is we have to find out the static margin. So what is the static margin and why we need to understand? So static margin is the difference between the CG and AC of the or the neutral point of the wing. So if you see here that from here, if this is the CG and there is the AC, so this is called XCG and this is called from here to here, it is called XAC. And if you divide it by your chord, so it will be divided by C. So it is a X bar CG and this is the X bar AC. And this AC is also called the neutral point. So the static margin is the difference between the X bar CG minus X bar NP. X bar NP. And this is a very important parameter to understand that how much stability we have. As you have the more amount of your static margin, that much amount of stability will be persisting in the system. So as a this design engineer, we have to understand that how much static margin should be present in the aircraft system, and accordingly we have to see it. So let us see that we have seen already that the aircraft, this is the Cm alpha AC. This is the Cm alpha AC. This you can also write AC here. So this dCm by d alpha of aircraft is the summation of CLW, coefficient of lift of the wing, in bracket XCG minus C bar minus XACW by C bar plus Cm alpha fuselage minus neta VH CL alpha T 1 minus d epsilon by d alpha. Now I will try to find dCm by dCl. So you know that we have drawn always Cm by alpha, but for steady state case and for the linear case, we can write alpha is equal to CL also, up to some angle of attack. Wherever you are having the straight line up to 15 degree to 16 degree angle of attack, you can, alpha is approximated as a CL. So now we want to convert and we want to find dCm by dCl, and what will be the dCm by dCl. So here we can do that dCm by d alpha into 1 by dCl by d alpha. So here you can see if we can cut this and this, so we will get here dCm by dCl. So here we have taken the assumption here that the CL alpha W is equal to the CL alpha of aircraft, and alpha of the wing is equal to angle of attack of the aircraft. These two assumptions we have here taken, and we have so here dCm by dCl is equal to here XCG by C bar minus XAC by C bar plus Cm alpha Fs divided by Cl alpha wing minus Vn neta Vh Cl alpha T divided by Cl alpha wing 1 minus d epsilon by d alpha. So now we have taken this here that dCm by dCl is equal to XCG by C bar minus, so this all become opposite sign, so XAC by C bar minus Cm alpha T divided by Cl alpha, here it is Fs, Cm alpha Fs divided by Cl alpha W plus neta Vh Cl alpha T divided by Cl alpha wing 1 minus d epsilon by d alpha. And you might have seen that our previous, you can see this one is our neutral point. So this neutral point we have shifted here. So dCm by dCl is equal to XCG by C bar. dCm by dCl is equal to XCG by C bar minus XNP by C bar. So this is equal to XCG X bar CG minus X bar NP. So we can take here minus XNP minus XCG. So this XNP minus XCG is called the static margin, and it should be, so it is given as a minus. So dCm by dC alpha, so dCm by dCl, it should be negative of Sm. If it is a negative, then it is a statically stable. Statically stable. So if suppose it is given that the static margin is, here I have drawn a plot of Cm versus Cl, and you know the trim point, this is the Cl trim point, Cl trim, this Cl trim if you know, and if you know the Cm naught, you can find out the slope. In case it is a 0.6 and the slope is 0.1, so you will get 0.06 as a Cm naught. So here if you know the slope, if you know the trim point, you can get this Cm. If you know the Cm or this thing, you can if you know the two things, third thing you can find out. Here it is shown here that this is your leading edge of the main wing, and here from here to here is X bar NP, and from here to here is a X bar CG. If these two things are there, the summation of, or the difference between minus X bar NP minus X bar CG, so here this you can see that XNP, if it is more than the XCG, it means if the neutral point is ahead, or this neutral point is behind, or the CG point is ahead of the neutral point, you will get Sm negative. So dCm by dCl will be negative, and if you are getting dCm by dCl is negative, it means your system is statically stable. So this is the importance of the neutral point as well as the static margin. We should understand that static margin is very important. And if I see this aircraft, so here is your leading edge of this thing. So if we compare from here, CG is here, NP is here. Means neutral point is behind the CG if it is there. So dCm by dCl will be negative SM. The static margin will be negative, and static margin is always represented in percentage of chord. So here, if you see here in this question, we have got that dCm by dCl, dCm by dCl, we got as a minus 0.1. It indicates that it is a 10% of the mean chord line. Okay, so 10% of the mean chord. So if this is the chord, this is the airfoil, and this is your C bar, so it will act 10%. It is, if CG is here, this is the CG, and this is the AC. This is called SM, static margin, and this SM is 10% of the C bar. This minus indicate that CG is ahead of the neutral point. So it should be very much clear. So if CG is ahead of the neutral point, you will get dCm by dCl is equal to negative static margin. If you are getting the negative static margin, then only system is statically stable. So that we have to keep in mind very much clearly, that this state of condition we should be able to maintain. Okay, further I am just discussing about the neutral point. So we are continuing how Cm alpha can be used to see the statically stable computed to Cm naught and the Cm alpha for full airplane. Another important thing is neutral point. Neutral point is that CG location which the aircraft becomes neutrally stable is called the neutral point. In mathematical form, dCm by d alpha is equal to 0 or dCm by dCl is equal to 0. We are talking about here stick fixed case only. So here we can see the case, how these things are happening. Floating of the elevator not allowed in the stick fixed. And here we can see that the location of CG at the point 1, and here is the point 2. AC is here. This Cm will act, Cm alpha will be negative. dCm by dCl is equal to negative, and dCm by d alpha is also negative. As long as this aerodynamic center is behind the CG, dCm by d alpha will be negative, or Cm will be negative. As long as the CG is ahead to AC, it will have a stabilizing effect. The point when aerodynamic center and the center of gravity coexist, then it is called the neutral point. So here this you can see in this diagram, the AC and CG both are in the same point, and then it is called the neutral point. Okay, so this is the understanding. Another understanding, we have to see that what is the effect of distance of center of gravity and the aerodynamic center. Here I have shown one wing, and this wing is reflex wing. It is called the reflex wing. In this reflex wing, this is the, so what is the importance of this wing? This reflex up to here, this wing is generating Cm in this direction, but this reflex is trying to balance this Cm, and it is making as a stable aircraft. So that is the purpose of this thing. Normally, if you see here, the CG position is here, the position 1, then position 2, position 3. Okay, and here just if your CG is located far ahead from this aerodynamic center is here, so in this case, this reflex is making Cm naught as a positive. Otherwise, if you see only this much, it is a negative. So, in the C1 case, the Cm alpha of this is in the negative. So, the plot 1 at the CG1 location is like this. If you shift from 1 to 2 here, the slope of this slope is reduced. If you go to point 3 here, further slope is reduced. As and when the CG and AC are each other coinciding, you will get a straight line. In this, it becomes a neutral point, and in the neutral point, you will get Cm by DCL or DCM by D alpha is equal to 0. So you will not get any slope. So it is shown here. So you will get Cm versus alpha or CL straight line. Further, if you make the center of gravity at the point 4 here what will happen now? It is changed to in this direction. So it is a positive. So this you can see, it is the point 4 and this is the unstable plot. So aircraft will be unstable if the CG is shifted behind the aerodynamic center of the aircraft. So this CG location at which DCM by DCL is equal to 0, aircraft becomes neutral point. So this AC will become neutral point, and this is the limitation of the center of gravity. At no cost, your CG should not go behind the aerodynamic center, and if it is going behind the center, this aerodynamic center, your aircraft is going to be unstable. So here it gives very important thing that if you see in this aircraft, we are taking all the measurement from the leading edge of the wing, and if here is your leading edge, this one, and here is the center of gravity, and here is the aerodynamic center. If you are shifting this center of gravity towards the backward, towards the aerodynamic center, slowly the slope of your curve will be reducing. And as and when the center of gravity of the aircraft is coinciding with the aerodynamic center, and if any wind is coming or any gust is coming, aircraft is flying like this, gust is coming, it will maintain in the same position without any disturbance. If you remove the disturbance also, and once it is disturbed at whatever angle, aircraft will maintain the same angle of attack or same pitching motion, and it will continue if center of gravity and aerodynamic center are in the same point, and that point now becomes the neutral point. So that is the importance. So at no case, the aerodynamic center should not be behind the aerodynamic center. If it is like this, then it will become, if it is disturbed, aircraft will go away from its neutral position. So that is the importance, and we have to take care of this before we design the aircraft. Okay, now what happens if CG is behind the aerodynamic center? Then the aircraft will be statically unstable case. Unstable does not mean uncontrollable. If the aircraft is unstable, it doesn't mean that it is uncontrollable, because the fighter aircrafts are statically unstable. How do the aircraft, if CG is ahead, then aircraft will be stable. Now if CG is coinciding, then airplane will be a neutral stable, and if CG is behind the AC, the aircraft will be unstable. So we can put CG some degree behind to aircraft and still we can maintain the stability due to the tail effect. This tail here, this tail will try to make the, if AC is here and CG is here, so here it will be like this and this tail will make like this. So anti-clockwise, this is the clockwise and this is the anti-clockwise. Both moment will be countered. In this case only, we can make the aircraft stable if CG is behind the AC only when tail is fitted. If tail is not there, it is not possible. Here we can see the same explanation here, that this is the FRL, fuselage reference line, and here is the aerodynamic center of the wing, and here is, it is shown the center of gravity of the aircraft, and here is the aerodynamic center of the tail. So what will happen in this case? So if you see, by putting the appropriate tail, we can get a stable case. Assume it is not there. So what will happen here? If CG is here, your moment will be Cm alpha will be positive and Cm naught also will be positive. So if aircraft is flying like this, this is the aircraft and this is the alpha. So if it is positive, it will go away. Cm alpha will go away. So it is an unstable case. But how to make it stable? Because we want Cm naught also positive. And if we keep aerodynamic center behind the AC, our Cm naught will be also negative. To have the static stable, we should have this Cm naught. This is the Cm naught, also it should be positive or greater than 0. So this can happen only when aerodynamic center is ahead of the center of gravity. And if it is like this, the tail is playing very important role. Tail will generate a lift in this direction and this lift will make a Cm alpha negative and this Cm alpha negative and this Cm alpha positive. If both are equal, aircraft will be neutral stable, and if Cm alpha of the tail is higher than the Cm alpha of the wing, it will nose down tendency. That is why we should try to make in such a way that aircraft, this tail we have to design in such a way that this tail should provide the moment in opposite direction or in anti-clockwise direction, and it should counter the moment of the aircraft wing. So by putting the appropriate tail, we can get stable aircraft. Now we can calculate the neutral point. So this we can see that x neutral point is equal to x AC of by C bar plus neta VH CL alpha T by CL alpha W 1 minus d epsilon by dl alpha. Assume you got the 0.5. Assume by putting all this value, you got x and p is equal to 0.5. So what is the meaning of 0.5? So just I am explaining here. So here the distance between AC and CG, the distance between AC and the CG, so XAC minus XCG divided by C bar is equal to 0.5. It means if this is the CG from here to here, this much distance, this distance is 0.5 between these two. So that is the, and here in this case, the Cm naught will be positive here, and this is the trim point, and this is the Cm alpha less than 0. So we can, so many of things are now clear and understand the physics behind the design of the aircraft. Now the fuselage contribution, this we can see that how the fuselage is behaving. So in this we can see that dCm by dCl alpha of aircraft is equal to summation of the dcm by dcl of the wing plus dcm by dcl of the tail plus dcm by dcl of the fuselage. And this all summation, if it should be like this, that cm should be greater than 0 and cm alpha or cm cl, it should be less than 0. If you see the fuselage, it is made of cone, then a cylinder, and then here bow tail. And if you see here the motion, this is providing here cm alpha greater than 0, cm alpha greater than 0, and this is cm is equal to 0, assuming, and this is also producing cm alpha greater than 0. So the total effect of your fuselage is 2 in this direction, and this total is cm positive. So the effect of fuselage is to create instability. It is not useful for getting the positive, the negative cm alpha. Mostly this bow tail is 7 to 9 degree tapered in this, and it is opposite to this cone. So it is generating the lift this in this direction. It is a CL, and the moment is in this direction. Okay, now these methods to calculate fuselage effect. So here this is drawn as a length, total length L, and this is the highest or maximum width or D. This is the nose, and here is the CL alpha. So here this CL alpha is equal to 2 into K2 minus K1, where K2 minus K1 ranges from 0.85 to 0.98, and this is called the Monk factor, and this condition is only applicable for L by D greater than 4. This CL alpha fuselage, mostly it is 1.8 radian per radian, or you can assume as a 2 per radian. Based on the references, this S reference, area of the reference is equal to pi d max square. Here is the d max square by 4, or pi d square by 4. So CL alpha S is equal to 2 pi d square max by 4 divided by area of the wing. So dcm by dcl is equal to k w square, f means fuselage, length of the fuselage divided by area of the wing into chord, then CL alpha W, where LF is the total length of the fuselage, WF is a maximum width of the fuselage, and SW is the area of the wing, and C is the chord of the wing. So in this way, and K is a number, and it is depend upon this plot. So here we can find out the location of the CG. This is the 10%, 20%, 30%, 40%, and accordingly we will get this value of K. So if you know this location, you can get from here. This K value is 0.03 typical value. There are engines, landing gears, fuselage always contributing to the destabilizing effect, and then it should be clear in the mind. So these are my references I have taken from NPTEL lecture of Aircraft Stability and Control by Professor A.K. Ghosh from IIT Kanpur, and this you can log in to this. And thank you very much. For any questions and the queries, you can log into yddwivedhi@gmail.com or YAGYADWVEDhi@IARE.ac.in. So in this, any questions you can send me in this. I will try to explain any doubt existed. Okay, thank you very much for joining the class. We will be meeting for a new class very soon. Till then, goodbye, see you, and thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.